Hi, let's wait for a few minutes for others to join and then we will begin the session. Hi, can someone confirm if I am audible and the screen is visible? Okay, thanks. Okay, I think we can start today's session. So, in the previous sessions, what we have covered is basics of number system, uh, combinational logic, basic logic gates, floating point representation. Then we covered introductory sequential circuits, and we did some problems related to sequential circuits as well. In today's lesson, what we are going to in today's session, what we are going to cover is something related to uh, interface electronics. Okay, so basically what we were studying till now is related to digital electronics, but the real world is analog, right? So whatever computation or whatever processing that we are performing in the digital world, it has to somehow interface with with the real world, right? And the real world is analog. We can't listen to something called as digital music, so it won't make any sense to us. So we will need something to convert the digitally processed data into something analog, right? And similarly, we need something to convert the analog data. Like, let's say we are uh, hearing a we are let's say the microphone, right? So it is capturing the analog signal, the voice, whatever I am speaking. It is converting it into digital signal, and that is being transmitted, right? So we need analog to digital converter and digital to analog converter, right? So these components are called as data converters, which convert data from one form to another, right? So before starting today's live session, I would like to cover a I would like to summarize a few things which is related to Mealy machine and Moore machine. So we have one question related to that in today's session, and then also I'll give you a brief summary about DAC and types of DAC that has been covered in the lecture, and ADC. Okay, so starting with Mealy machine and Moore machine. So Mealy machine is something in which the output is a function of present state and present input, whereas Moore machine is something in which the output is a function of the present state only, right? There are a few advantages where Mealy machine is used, then there are a few advantages where Moore machine is used, right? Mealy machines, they need fewer states, okay, and they react in the same cycle, okay, but Moore machine is more safe, yeah, because they react in the same cycle, so they need not wait for a clock, right? But Moore machine, it is actually a bit safer because the output changes at the clock edge, okay. So that is Moore machine. And yeah, so now let me summarize something, a few lines about the data converters. So it's basically forms an interface between your analog and digital world. And why exactly are we talking about analog when everything, like we are listening about digital revolution everywhere, right? But the digital revolution is not possible without analog, okay. So the world is analog, and at the heart of this digital revolution is actually analog electronics that is sitting. So to get the data into digital form, we need something that is called as a ADC, and to get back, to make understandable representation of the digitally processed data, we need a DAC, right, that will convert the digital signal into analog signal, okay. So in this particular course, the two DACs that were covered is binary weighted resistor DAC and R2R ladder DAC, okay. And binary weighted resistor DAC, it uses a op-amp, okay, summer, and it has resistor weighing from 2R, 4R, 16R something. So it's a weighted resistor, and that will be connected to the input bits, which will convert into your analog signals, okay. And so binary weighted DAC, the pros are that it is having a simple construction, right? So you have R2R and an op-amp acting as a summer, but the negative part is, let's say you have something related to 4 bits, right? So you will need a 16R, and you will also need a small normal 1R, right? So there's a huge difference in the range of resistance that is needed, okay. On the other hand, we have something called as R2R ladder DAC. So it only needs 2 resistor values, R and 2R, okay. But then the issue with that is the conversion speed is low, okay. Then let me tell you about one term which is related to DAC. So there are many terms actually related to settling time and everything, but in today's tutorial, so we will need this particular term. So we have something called as a resolution, okay. So resolution of a DAC is basically the smallest analog increment that is corresponding to 1 LSB of a DAC, okay. So with this basic introduction, let us start with today's live session, okay. So the first question is related to ADC. So how many comparators are required for a 3-bit flash type ADC, okay. Okay, so flash type, yeah,
7.
yeah, correct. The answer is 7. So we will see how we arrived at this thing. So let me tell you about what ADCs are present, means what ADCs are covered in this particular course. So in this course, it was covered a successive approximation ADC, a flash ADC, and a dual slope ADC, okay. So in flash ADC, what happens is we have a set of resistor, okay, and it is connected to op-amp, right, a comparator. So one end of the comparator goes to that reference voltage generator that is basically formed using your resistive divider network, okay. The other end goes to the V input, okay. So basically when I say that 3-bit flash type ADC is needed, so it means there will be multiple inputs which will be going to an encoder, and that encoder will give you 3 bits as output, Okay, and so this general formula will help you in deciding how many comparators will be needed. So let's say we have a n-bit flash ADC. Okay, so the number of comparator needed is 2 power n minus 1. So because it is a 3-bit flash, so n is equal to 3 in our case. It is 8 minus 1 is equal to 7. Option A is correct. Okay. Okay, so moving on to the next question. So in this question, what we are asked to find out is what is the V out. Okay, and it is given that ABCD is equal to 1010. So 1010 actually represents the digital voltage, but what 1 corresponds to is 2.5 volts and 0 corresponds to voltage of 0 volt. Okay, so let us think how to proceed with this question. And while solving problems related to data converters, so you have to assume that this node, okay, is actually virtual ground. Okay, so it can, okay, so you can assume that this is actually at 0 potential. So what you can do is, you have A, so we have this value 1 0 1 0. It means A is at a potential of 2.5, B is 0, C is 2.5, D is 0. Okay, and using that we have to compute what is the V out. Okay, so first I will go through the logical process, how we need to do. Second, I will give you a shortcut, that is directly using the formula. Okay, so what I am going to do is, I am going to use something called as KCL at this particular node. Okay, so KCL will be basically what is the current that is flowing through this branch. So this current has nowhere else to go, so it will go through this branch, right? Because this is at a very high impedance, so current won't flow and current will go through this path. So what is going to be the current? I1. Okay, basically what I want to say is I1 is equal to Ix. Okay, so what will be the total current I1 flowing through this? So there will be no current flowing through this path because both the potentials are 0. There won't be any current flowing through this path as well because both the potentials are 0. So we have only two paths which is contributing to the current. So to find out the current, we know that current is equal to V by R. Okay, so V refers to the potential difference between the two nodes. Okay, so let me start with node A. So the potential difference is 2.5 minus, this is 0, by 1 kilo ohm, plus at node C we have 2.5 minus 0 by 4 kilo ohm, okay, is equal to Ix. Okay, so Ix is flowing in this direction, so it means the potential difference is 0 minus, this is at a potential V out. Okay, and what is the resistance connected between these 2 points? It is 1 kilo ohm. Okay, so let us solve this, simplify this equation. So it will be 2.5, okay, and k is common, so I'll cut k everywhere. So 2.5 plus 2.5 by 4 is equal to minus V out. Okay, so we have 2.5 into 4, it's 10 plus 2.5 by 4 is equal to minus V out, or V out is equal to 12.5 by 4, sorry, minus 12.5 by 4 is equal to minus 3.125. So this is our answer. Is everyone clear with this method? Does anyone have any query?
Please repeat this process.
Yeah.
Again, please.
Okay. So what I did is, it is given to us that ABCD is actually 1010, and 1 corresponds to 2.5 volt logic and 0 corresponds to 0 volts. Okay. So what I did is I did the corresponding mapping here. Okay. Then what I am going to use is, so I notice actually at the op amp is assumed to be ideal. So an ideal op amp doesn't take in any current. So it means, so notice this junction. Okay. So this is current I1, this is current IX, and there this, let me call this I0. Okay, and this is the terminal of the op amp. So what happens is I0 is equals to 0 for an ideal op amp. So if I0 equals to 0, where will I1 go? So I1 has only one path to go, so it means I1 is basically IX. Right? And what I do is, now I compute I1, and let me see what are the sources that are contributing to I1. So I see that B and D are held at 0. Okay, and this node, this particular node, is actually at virtual ground. So this is a property of an ideal op amp, that this node, due to negative feedback, it will be at virtual ground if the other node is connected to ground. Okay, so it means I know this potential to be 0. I know B and D are not going to contribute anything because the potential at V, B and D, it is 0. So there won't be any current flowing through B and D. So the only two branches that is contributing to the current I1 is actually A and C. Okay, so what will be the current through A branch? It will be the voltage difference between the two nodes here and here, and the resistance divided by the resistance, right? So the voltage difference is 2.5 minus 0 divided by the resistance, that is 1 kilo ohm. Okay, that is the current through A. Similarly, the current through C is voltage difference across 2.5 and 0. Okay, divided by 4K. 4K is the resistance that is connected here. Okay, so this is actually I1. Okay, and I1 has to be equal to IX, right? And what will be the value of IX? I'll find out what is the potential difference first, that is 0 minus V out by 1 kilo ohm, that is the resistance connected across these two terminals, right? And after doing that, I just solved these equations, okay, step by step, and I found out that V out is equal to minus 3.125 volt. Is that clear?
Yes.
Okay. So this is, so I wanted to cover this method because I want you to learn what is the rationality behind, like how do we come up with a simpler formula, because I have seen that there was a simpler formula that was written. So you, to solve questions, you can use this formula, but I'll suggest you to know what is the actual logic behind it. Okay. So let me give you a simple formula. Okay. So what you can do is you can use this formula directly and arrive at your answer. So in this case, what you do is, RF is your feedback resistor, okay, that is 1 kilo ohm, and R4 is the resistance that is connected between terminal A and ground. Okay, so similarly you just replace the values and you will obtain V out directly from this formula. But how does this formula come? It comes from these equations itself. Okay, you can directly use this formula and compute the value of V out. You will observe that the value is same. Okay, I hope this question is clear, and the logic how we arrived at this solution is also clear.
Yeah.
Okay. Okay, moving on to the next question. Okay, so which of the following ADCs takes the maximum time for conversion? So this is actually a fact-based question. So for the conversion time, you can remember this. So dual slope, flash, successive approximation. Okay, so flash is very fast, and that's why the name flash. Then next is successive approximation. So let's say it is medium. Then dual slope is the slowest. Okay. Speed of conversion. Okay. So this question asks which ADC is going to take the maximum time for conversion. It is dual slope, right? Because it is going to be the slowest. Okay. Now, what is asked is what is the resolution of an 8-bit R2R ladder DAC? Assume the reference voltage to be 5 volts. Okay. So, in the beginning, I defined a resolution, right? So, here we are supposed to find out what is the resolution of an 8-bit R2R ladder DAC. Okay. So, what is given to us is total number of bits is 8. Okay. And the reference is 5. So to find out the resolution, what we need to do is Vref by 2 power n. So can anyone calculate this and let me know what is the answer?
For D option 18.53.
Sorry, can you repeat?
D option 19.53.
Okay. Okay, so I got one response. Is there any other response? Okay. So this will be basically 5 volt by 2 power 8. So 2 power 8 is 256. Yeah, that will be close to 19. Not close to, that will be exactly 9.53. Yeah, option D is correct. Okay, so yeah, I got a different answer as well. So probably you would like to recheck Amit, 0.26, 0.25. Here, okay, I think, yeah. So Vref is actually 5 volt here. So maybe you took 1 volt, I guess. Okay, so that was for the resolution. Okay, then the next thing is we are given a R2R DAC and we have to compute the output of this following circuit. It is given that the digital bits are B4 is equal to 1, B3 equals to 1, B2 equals to 1, B1 equals to 1, and the reference is 8 volt. Okay. So if B1 equals to 1. Okay, so this is the configuration in which it is connected. Okay, so in these type of DACs, what happens is they use a switch. Okay, and the input to that switch is the digital bit. Okay, and in this case, V0 is equal to plus okay, so this is going to be the output. So for deriving this particular equation also, you need to use the same thing. Okay, so you need to find out the current I1 here. Okay, and here there won't be any current going, and this is Ix. Equate both and you will be able to find out what is V0. Okay, so I'm giving you the final equation that you can directly use to arrive at your solution.
Option A is the answer?
Option A. Okay, Vref is given as 8 volt.
Maybe.
So 8 plus 111 8. Okay, yeah, so one answer is option A. Is there any other answer? Anyone else would like to give it a try? Okay, actually option A is the correct answer.
Actually, how you took, sir, 16 or 8 or 4 or 2 or how you took, sir?
Okay, so can you see the current that is flowing through this?
Okay.
Yeah.
Okay, sir, understood.
Yeah. Okay, so minus 7.5 volt is the correct answer. And to quickly arrive at the solution, you can directly use this formula. Okay, so there's an R here. Okay, otherwise if you want to know how it came up, so just like in the previous case we solved, okay, so by using KCL at this node, so you can similarly derive this particular equation as well and obtain what is the V out.
Can we take V reference common from
Yes.
this equation?
Yeah, we
So
can
that
take
will
V
be easy.
reference by R common, so RR will get cancelled and we will be left with V reference into B4 by 16 plus B3 by 8 plus B2 by 4 plus B1 by 2. Okay, so the next question is a 4-bit R2R ladder DAC produces output voltage of minus 5 volt for the input 1001. What is the reference voltage? Okay, so we will use the same formula because it is basically a R2R ladder DAC. Okay, so what we are going to do is, okay, let us simplify and what we will do is V0 is equal to minus, we will take Vref common, okay, minus Vref R by R into B4 by 16 plus B3 by 8 plus B2 by 4 plus B1 by 2. Okay, and we will use this in the next question. Okay, so here it is given that B3, B2, B1, B0 is 1001. Okay, so what I will do is, so 1 means this is going to stay, this is 0, so this will go, this is 0, this will go, this is 1, so this is going to stay. So in our next question what we will have is minus Vref into 1 by 16R plus 1 by 2R into R is equal to minus 5. Okay, then we can cancel out R, so we just need to find out what is Vref. Can anyone calculate and let me know what is Vref?
Mine 8.89.
Correct. So this is 8.89. So it will be 5 into 16 by 9, which is basically 8.89 volt. Okay, so 8.89 volt is the reference voltage. Okay, so based on the facts that we discussed in the beginning of the session, so can someone try this out? So I mentioned that R2R ladder had a disadvantage, right? So what was it?
Lower conversion speed.
Correct. So
So B is the right answer.
Yeah. Okay. Any other answer? Actually, I saw another answer popping up on my screen. Option C. Option B. Okay. Yeah, actually option B is correct. Okay, it has lower conversion speed. So R2R ladder DAC. Okay, so one of the options that one student shared is option C. So option C is not correct. It is actually binary weighted DAC that will need a high precision resistor, and not an R2R DAC. Okay, so I hope that is that point is clear. And option D is obviously not correct, because binary weighted, the name suggests that it will need multiple resistors like 2R, 4R, 16R, and that was the issue, right? We needed a range of resistors to implement this particular DAC. Okay, so only option that is correct is option B. Okay, so moving on to the next question. So the flash ADC that we spoke about in the beginning of this session, right? So this is the flash ADC, and here you can see that we have a resistor, complete network of resistor connected in series. And so what you can observe is, let's say I have two resistors, okay, and this is connected to VDD, okay, and this is connected to ground. Let me call it R1, let me call this R2. Okay, so can someone tell me what is Vx in terms of R1, R2 and VDD?
VDD into R1 by R1 plus R2.
Correct. So Vx is equal to VDD into R1 by R1 plus R2. Okay, so this is actually called as a resistive divider, and that this is the basic principle behind your flash ADC, that each of these nodes that is connected, that is generating the reference voltage, is basically behaving as a resistive divider connected at various nodes. So let me count how many resistors are there. 1, 2, 3, 4, 5, 6, 7, 8. There are total 8 resistors. Okay, so it means if I take the voltage across this point, okay, can you see the point that I am encircling?
Yeah.
Okay, so the voltage across this point will be actually R by the sum total of all the resistance. Okay, so the sum total will be 8R into Vref. Okay, similarly, so this potential is going to be, Vref is given as 16 to us, so this is going to be 16 by 8 or 2 volt. Okay, similarly this is going to be 2R by 8R into Vref, right? Because two resistors are connected to the ground and the remaining the total resistance is 8R, so this is going to be 4 volts. Similarly, this is going to be 6 volt, this is going to be 8 volt, this is 10 volt, this is 12 volt, this is 14 volt, and anyways Vref is given as 16 volt to you. Okay, so you can see that these nodes are actually acting as one of the inputs to the comparators. Okay, U7 to U1 is are actually comparators, right? And one end of the comparator is connected to V input, that is the incoming signal. Okay, and the other input is connected to the reference voltage. Okay, so it means, let me assume, okay, so let me draw a comparator like this, Vx and Vy. So can anyone tell me when will this output be 1?
Vx greater than Vy?
Correct. So if Vx greater than Vy, then out is equal to 1. Else out is equal to 0. Okay. So this is the rationality which we are going to use while solving questions related to flash ADC. Okay. So this is how the entire comparator chain is going to operate. Okay. So it is given to us that V input is equal to 10.13 volt. Okay, so it means this potential V input is equal to 10.13. The positive terminal is at 10.13, but here we observe that the negative potential is at 14 volt. So what will be the value of D7?
0.
Correct. Okay, so for D6, this node is at 12 volt and this node is at 10.13 volt. What will be D6?
0.
Correct.
0 again.
Yeah. So till what till what point will these bits be 0? Any generic point?
Till this point, I think.
Okay, so I'm looking for a generic statement like Vx could have the V in could have been anything. So what I am looking for is, like, if I want to make a very generic statement like let's say V in is equal to X, and then I am looking at till what point I need to ensure that the comparators are going to be 0. It is basically till the Vref is greater than, if the Vref is greater than V in, till that point the comparator output will be 0, right?
Yes.
Okay, so from that observation we see that anyway, because this is 14 volt, it would have given 0. This is 12 volt, it would have also given 0 because this is greater than V input. Okay, then but this is less than that, less than the input. So here it is 10.13 and here it is 10 volt. So it is going to be 1. Right? And what will the rest of the bits be?
1.
1.
Correct. Because anyways, the rest of the reference potential that is generated is going to be less than Vn, right? Because we see an increasing trend when we move from down to the top of the ladder, right? Okay. Okay. So we have generated D7 from D7 to D0. Now it comes priority encoding. Okay. So what does priority encoding do? We covered it in one of the tutorial sessions. So can someone tell me what does priority encoder do? Okay, so priority encoder, basically it assigns a kind of priority that if the most significant bit is high, then without bothering about the least significant bits, the output is going to be the encoded form of the most significant bit. Okay, so it means if I have 1 1, okay, so if the most significant bit, that is D5, is set, so I need not bother about the rest of the bits. So the output has to be 5 in binary. Did you get this point? Yeah, the answer is B, correct. Is everyone clear about the priority encoding part?
Please repeat.
Yeah, so priority encoder, basically what it does is, so whatever is the input, so if the most significant bit of that input is high, without bothering about the remaining least significant bits, the output is going to be the value equal to the binary of the most significant bit, right? So in this case, as D5 was 1, so we did not even bother looking at the rest of the bits, that is from D4 to D0, because of this priority encoding part. Is that clear?
Yeah. Now it's clear.
Yeah. So this is going to be 101. That is 5. That is option B. I hope this part is clear. Okay. So moving on to the next question. So the next question is also similar, and okay. So the first step whenever you see a flash ADC is compute all the reference voltages. Okay. So can anyone tell me what are these voltages? So we will start from the top this time. Okay. And this is also a 3-bit output, so total there will be 7 comparators and 8 resistors. Okay, and Vref is given to us as 16. So what is this voltage?
The same as we calculated before, the 16, 14, 12.
Correct. So this will be 14 volt.
Yes.
Similarly, this will be 12 volt.
12 volt.
This is 10.
10.
And it will go all down till 2 volt.
2 volt.
Okay. And so here also, let us see what is the V input. So step 1 should be calculate the reference voltages. Okay. Step 2 is identify where your V in is located. Okay. So can anyone tell me, so where does V in lie?
In between 10 volt and 6 volt.
In between, okay, the range is quite high, so let us reduce it
8.
to, yeah, okay,
8 to 6.
correct. So it lies here, 8 volt to 6 volt. Okay, so what does it mean? What do we observe in the previous case? That as long as Vref is greater than V in, what is going to happen?
Comparator output.
Comparator output first one will be 0.
Okay.
Next one will also be 0.
Okay.
Next one will also be 0.
Okay. And what will happen to D4?
D4, 8. This is also be 0.
Okay.
3 will become 1.
Correct.
Next one.
Yeah. Next everything will be 1, 1, 1, and this is 0. Okay. So
this is 3.
Yeah, correct. Because the D3 bit is high, so the output is going to be 3. So 3 in binary is 0, 1, 1. That is option C. Is this clear?
Yes.
Yes.
Okay, so based on the previous questions that we solved, can anyone tell me what is going to be the size of priority encoder for 4-bit flash? So let's do it step by step. So how many comparators will be needed for 4-bit flash?
4. 16.
Think once again.
15. 15.
Correct.
15. 2 power n minus 1.
Correct. So 2 power n minus 1 comparators are needed. So total 15 comparators will be needed. Okay. Okay, let me bring the previous question again so that you can see. Okay, so now tell me how many resistors we will need. For a 4-bit flash ADC.
16.
Correct. So there will be 16 resistors. Okay. So 16 resistors will imply how many reference voltages? So this is a tricky question, but yeah.
One reference voltage.
No. Okay. So reference voltage, I am referring to the node voltages, reference node voltages, like this. -15. Okay, that's correct.
-1.
So what should be the input dimension of the encoder? So this is my encoder. Okay. So what should be this input dimension?
16 by 4.
Correct. So the answer is correct. But what should be the input dimension here? Correct. So because one of the bits is going to be anyways 0 and rest we have output from 15 comparators. So total inputs needed is 16. Okay, and it is given to us that it is a 4-bit flash. So the output is going to be 4-bit, right? So the answer is 16 cross 4. Is this clear?
Yes.
Okay. Okay, so the next question is also related to a fact-based. Okay, so we covered this fact at the starting. So can anyone tell me what is the correct answer for this question? Yeah. Okay, that's the correct answer. That binary weighted resistor DAC requires high precision resistors. Okay. Okay, and why is option D not correct here? Can
Multiple resistors are required.
correct.
Multiple types.
Yeah. And why is option C not correct?
Because we don't use any transistors here. We have passive components.
Yeah, we have passive components, but actually we are using switches, right? So in the DAC, if you observe, okay, let me show you where the transistors actually are. So, okay, so let me give you this example. So here, can you see the red box that I made?
Yes.
Yeah. So actually these these connecting points are basically transistors. Okay, so transistors can behave as a switch.
Yes.
Right. So to implement these switches, what we do is we use transistors, and the input to the gate of these transistors is basically your binary input. This B1, B2, B3, B4 that you are observing, right? So these actually go to the gate of the transistors. So transistors are there. Okay, but we will never prefer a high switch resistance in transistor. Okay, because if we are going to prefer a very high switch resistance, then it will mean that it is going to distort our output. Okay, so for that reason we always prefer transistors which is used for switching to have as low resistance as possible. Okay. Okay, so the next question is related to a sample and hold circuit. Okay, so sample and hold is actually a key element of what is called as an ADC, okay, analog to digital conversion. So in analog to digital conversion, what happens is you have a continuous time signal, okay, and we are going to convert it into digital signal. Okay, so based on your lecture, so can anyone tell me what is the first process in the analog to digital conversion?
Sampling.
Correct. So what do we do in sampling?
We're
Analog to the discrete.
Correct.
Yeah.
But
We're analog to discrete.
PAM. Actually, you're getting PAM.
yeah, okay. So when you mention discrete, so I can say, okay, so discrete can be either in this format, okay, otherwise it can be in this format. So whether are you referring to the vertical lines or the horizontal lines?
Vertical.
With respect to time.
Yeah, so discretization in time is called as sampling. Okay, and once it is sampled, that value is held for some time. Okay, and after sampling, what happens?
Input. Quantization.
Correct, quantization and followed by encoding. Okay, so this is the complete process that the ADC performs for converting any analog signal into a digital signal, right? First it will discretize in time domain, that is called as sampling. Then it will discretize in the amplitude, then it will discretize the amplitudes. Okay, so after discretizing the amplitudes, those amplitudes are mapped to corresponding digital values, which is called as encoding. Okay, so now let us focus on this question. So this question is related to sampling. So what is the most essential element in a sample and hold circuit?
Capacitors.
Correct.
Capacitor.
Yeah. Because the statement hold itself mentions that there needs to be an element which is going to have memory for some time, right? So that is the capacitor, and capacitor is widely used. So you can create a sample and hold circuit using a normal capacitor and a switch. Okay, so switch basically, as I mentioned, it's a transistor, and you apply a clock to that switch, so that will behave as an on off key kind of thing, and we need to ensure that the switch has a very least resistance, right? Okay, so moving on to the next question. So this is regarding Moore and Mealy machine. So can anyone try this question?
B. Option B.
Moore machine output depends only on the current state. Okay, then what does Mealy machine's output depend on?
Depend on current state and current input.
Correct.
Current input.
Yeah. So option B is actually correct. Okay, and is option okay? Yeah, other things are all also covered, I guess. So, okay, moving on to the next question. Okay, so as I mentioned in the beginning that there is a process called sampling, but can I say that, let's say I have a signal at 10 hertz. So can I sample this signal at 11 hertz?
Double of signal.
Okay.
Fs should be greater than twice of Fm.
Okay. Fs should be greater than
Nyquist
twice.
criteria, yeah.
Yeah, this is the Nyquist criteria. But why do we follow the Nyquist criteria?
If it is less than a signal, the signal will be lost.
Okay, the signal will be lost. And so can anyone tell me what is the goal of sampling?
To carry a signal, just like a modulation.
No. I have an ADC, okay, and it is going to sample the signal. But why do I need to sample the signal? Can't I directly quantize the amplitudes and just save it?
Yeah, we can't do the quantization directly because they will be using the either quantization method. Two methods will be used in the quantization, so we can't do the quantization directly. So we have to convert it to discrete, and then we want to do the quantization.
But let's say I say that there is a function which restricts the values to let's say 1.2, 2.2, 3.2, and so on and so forth. So
yeah, noise will be the granular noise and one more noise.
Is there any other answer? Anyone would like to give it a try?
At what time, what voltage is present, that we cannot tell.
Okay, yeah, that's a good point. Then there is another most important thing. So digital is basically having, like when you convert anything to digital, so there is bit width associated with it, right? And you cannot have infinite number of samples. So when I say that a signal is continuous, so it means you can assume that the sampling frequency of that signal is infinite, right? But if a signal has infinite samples, then I can't store them. So because of that, I need to sample the signals. But the sampling has to be done in such a way that we do not lose the signal. So what do I mean by do not lose the signal? I mean to say that whenever I want to recover the signal from the discrete values, I will be able to recover the signal. Okay, and that is what this Nyquist criteria tells us, that if you are going to sample at twice the maximum frequency component of the signal, then you will be successfully able to reconstruct the signal. Okay, so maybe you can use a DAC later on to reconstruct the signal back. Okay, so that is what the Nyquist criteria tells us. So if I say that the maximum frequency component is 10 Hz, then the sampling frequency should be
greater than 20.
Correct, greater than 20 Hz. Okay, so option B is correct. Oh, sorry, if this is at most, option A is correct, is at least twice of the maximum input signal frequency. Okay, so can the sampling frequency be 5 times the maximum signal frequency?
Yeah.
Okay, but it is related to bandwidth.
Correct, yeah, right. So it can be anything, but at least it should be. So at least is most important, because if you take any higher courses related to data converters, you will come across a class which is called as oversampled data converters. So in those data converters, what happens is you can sample at 16 times the Nyquist frequency, or 512 times the Nyquist frequency. Means this is done to increase the quality of this signal recovery. Okay. Okay. So in a dual slope ADC, which of the following element is not present? Okay, first tell me, is a sample and hold circuit present?
Yeah.
Yes.
Okay. Is a comparator present?
Yes.
Okay.
Counter, I think, don't present.
Okay. So counter is present in which ADC?
Actually, why ADC is having DAC?
Correct. So the correct answer is option C. Okay, we don't need a DAC in this dual slope ADC. Right? I hope this is clear, and I also hope the motivation behind studying data converters is clear, because oftentimes what I have seen is people who are pursuing digital, so they often tend to look down at the finer aspects of this data conversion circuits. But I hope that you are able to realize what is the necessity behind having a data converter, right? So yeah, so these were the 15 questions that I planned for today. So I'll go through all the questions that we did today, and if anyone has any doubt, so let me know. So the first question, it was related to the number of comparators that are required for a 3-bit flash type ADC. Okay, and it is 2 to the power n minus 1. Okay, so those many comparators will be needed, and later on we also saw like how to figure out how many number of resistors we need, and what is the dimension of the encoder that we are going to need in an ADC. And the next question was related to a DAC. Okay, and we were supposed to figure out. Yeah, Suresh, you have a question?
I mean, for the ADCs, right? In the previous question,
Okay.
do we have any other type of encoders at the output? I mean, in the flash type ADC,
Okay.
since there is no explicitly mentioned that ADC is a priority encoder or non-priority encoder.
Okay.
So in that case, so do we need to consider the comparators outputs, or else we need to consider that ADC output and then it is converted to encoder and then bits are coming out?
Yeah, you need to consider the comparator output that is going to the encoder. Okay, and the output of the encoder is the one that dictates the number of bits of ADC.
Right.
Okay, so let's say you have a 3-bit flash. The total number of comparator is 7, so the output, so the total number of bits would have been actually 7, right? 8, basically, because
Eight.
there is a 0 here, right? But
Yes.
we can't call it an 8-bit ADC looking at the comparator output. So because we are then wasting those bits, right? Because the same information can be represented in 3 bits notation.
Right.
So that's why we use an encoder to encode whatever information is available with us, to compress it into 3 bits, because each bit is going to expend some energy, some power.
Right.
Okay, so that's why whenever you say that this is a n bit ADC, it means the output of the encoder is n bit.
Okay.
Okay, does that answer your question?
Yeah, yes.
Okay, so in the next question, what we did is we observed a DAC that is given to us, and we were supposed to figure out what is the V out. Okay, yeah. So for this particular question, what we did is, whatever input is given to us, the first thing is map the digital input to analog values. So here we can see that logic 1 is mapped to 2.5 and logic 0 is mapped to 0. Okay, so that's what I did. I assigned 2.5 to those nodes where it is 1 and 0 to those nodes where it is 0. Okay, then to solve these questions, if you want to solve it quickly, then use this formula without giving a second thought. Okay, but if you want to, okay, so let's say you are stuck at a point when you think that why do I need to use this formula, how did this formula come up? So at that point, what I will suggest you to do is always remember that the comparator that is being used, the input is actually held at virtual ground. Okay, and the property of this ideal op-amp is that it does not suck in any current, right? So I0 is equal to 0, and I know this property that I1 is anyways going to the next to the output, right? So I1 is equal to Ix because there is no current going into the op-amp. So what you can do is, at this particular node you can use KCL, okay, and you will arrive at the formula. Okay, so the next thing is, so there are a few factual things that you need to remember at this point, because later on, let's say you think of pursuing a career in mixed signal VLSI design. Okay, so this field of study and design of data converters is actually dealt by a field called mixed signal VLSI design. Okay, because it involves both analog and digital signals, so the name mixed signal. Okay, for designing data converters and many other circuits related to that, the comparator design and everything. So that is this particular field. So when you start designing that, so there are a few things, there are a few facts that you need to keep in mind. So this particular course is going to form the base for that, and in the future maybe you can take up few courses related to CMOS analog VLSI design and stuff. So they will be very helpful because that's currently a very hot topic in the market, mixed signal VLSI design. So maybe if you find some time, you can Google it and search for a few online courses. There are few NPTEL courses as well, which is running parallelly. Okay, so basically, so in this case, so how does this fact help us? Okay, so let's say you are planning to use an ADC in any of your design. Okay, let's say you are not going to design that ADC. Okay, but you need to figure out that you have a bunch of ADCs, and for you what matters is the latency. Okay, so let me give you an example. Let's say that this particular application is related to let's say some remote surgery, right? So here the surgeon is using a scissor, okay, and that particular scissor, let's say I'm closing that scissor. After what instance is that particular closing action being reflected? Okay, that is of great matter to us, right? So we need to figure out what ADC will have the least minimum reaction time. Okay, so you need to remember this particular fact, that which is going to have the least conversion time, because as an engineer that is going to be your role. Okay, that you are going to tell them. Okay, I hope this particular motivation is clear, that why you need to remember these things. Okay, then the next question was related to resolution of this 8-bit R2R ladder DAC. And as I mentioned about a resolution, that it is the smallest measurable analog value, okay, analog increment basically, that is going to correspond to one least significant bit. Okay, and to figure that out, what you need to do is you have the Vref divided by 2 to the power n. Okay, and n refers to the n bit, and that is basically 2 to the power 8. Okay, and the next question was related to R2R ladder DAC, and to compute the value directly, we are going to use this formula.
Sir, excuse me, sir.
Yeah.
Sir, sometimes in last question,
Yeah.
it will be 2 power n minus 1. When will be the case, sir? I didn't get.
2 power n minus 1. 2 power n minus 1. Actually, I haven't come across anything where the resolution is 2 power n minus 1. But either way, what you can observe is whether you take 2 power n or 2 power n minus 1, the final result is going to vary by a very small number.
Okay.
So means basically 2 power n is a very large number in comparison to 1. So sometimes we also ignore the minus 1 part.
Okay.
So maybe that might be creating a confusion, but yeah. So yeah.
Is the question related to ADC or DAC?
Which
In
one?
that question, they are mentioning DAC. The previous one, yes.
Yeah, this is
R2 or
related.
later.
This is DAC.
Okay.
Okay, yeah. Okay, so the next question also we can simply directly use the formula, or else we can go through the long way of using KCL. But in this case, KCL is going to be very cumbersome, that you have to solve for each node which bit is 1. So directly you can use the formula to arrive at the solution quickly. Okay, so the next question was related to the formula that we used in the previous question, and we just substitute whatever was given to us. In this case it was V0 and the bits that were high. Okay, and we figure out what is going to be the Vref. Okay, so the next question was related to R2R ladder DAC and binary weighted DAC, and these facts were covered in the beginning of the tutorial. Okay, so next, whatever problems we solved were related to flash ADCs, and we figured out how to solve these type of problems. So the first step is figure out the reference node voltages that is going to the comparator. The next thing is identify where V in lies between what two reference voltages. The third thing is, when you have figured out what where V in lies, figure out the digital values, the D3, D6, D5 and stuff. The last thing is priority encoding based on whatever highest D5 is set. So DX is set. Okay, so figure out the binary value for X. Okay, and that will solve your question. The same thing we are going to do for so this is also this similar question. This is for practice. Okay, the next thing was for determining what is the dimension of the encoder that is needed, and we figured out that total 15 comparators are there. So there will be 15 outputs incoming to the encoder, and one output is anyways grounded, so the input is going to be 16 and the output needed is 4-bit. So it's a 16x4 encoder that is needed. Okay, then the next question was also factual and related to R2R and binary weighted resistor DAC. Okay, next thing was related to ADC, the sample and hold circuit that is used in an ADC, and obviously the capacitor is one of the most essential elements, not only in an ADC but any low power design if you go. So we hardly ever use inductor. Okay, it is always a capacitor, because the area that is going to be occupied in an by an inductor is going to be very high. Okay, the next question was also factual and it was related to Moore and Mealy machines. So okay, then the next question was related to sampling frequency following the Nyquist criteria, and if we don't follow the Nyquist criteria, then we are going to end up with something called as aliasing, and aliasing leads to undesirable components along with our signal which can't be separated easily, and we are going to lose our signal. Okay, so that is what that is why Nyquist criteria is followed, and Nyquist criteria states the minimum sampling frequency, so that's why the word at least is used. Okay, then the next question was related to which component is not present in dual slope ADC, that is basically DAC. Okay, so that brings us to the end of today's session. So I hope this session was useful and it will be useful for your assignments that you solved. So if there is any question, then I'll be available here for some time. Please let me know. Else we can wrap up today's session. Thank you everyone for joining. Is there any doubt, or does anyone want to discuss anything?
Yes, sir. Please explain the flash ADC type question.
Okay. Okay, so let me take this particular example for explaining. Okay, so let us start with what are the components that we will be having in a flash ADC. The first thing is a resistor, second thing is a comparator, third thing is an encoder. Okay, so what is the utility of a resistor? It is to generate the reference node voltages for that is going to the comparator. Okay, so now look at this particular example. Okay, so we have R1 and R2 connected in series, and I am taking the voltage Vx across R1. Okay, so if I am taking the voltage across R1, then Vx is going to be R1 by R1 plus R2 into VDD, or in generic term, let me call it Rx, and let this be a set of resistance whom I am representing as summation of R. So Rx by summation of R into VDD is going to be my Vx. Is this clear?
Yes, sir.
Okay, so next thing what I am going to do is, using this logic, okay, I am going to figure out these node voltages. Okay, so can you tell
Okay.
me what is going to be the voltage at this node? Okay, so you observe this, right? So this is actually ground.
Yeah.
Okay, and so let me call this as Vx. Okay, and the rest of the resistors as some Y. Okay, so using this, looking at this formula, what can you tell me about Vx? Okay, so basically Vx is the potential between the resistance in consideration and ground. Right, so Vx is going to be R by summation of R. Okay, so summation of R is this R plus this R plus this R. Okay, so total there are 8 R's. Okay, so it means summation of R will be 8R. Correct?
Correct. Okay, sir.
Yeah, into Vref. Okay, so this is for one potential. So next potential, when I try to find out at this particular node, now what will happen is the resistance that is connected with the ground is actually R plus R.
Okay.
Okay, so this R is now actually 2R. So it will be 2R by 8R into Vref.
Okay.
Okay, so on and so forth, I compute for each and every node that is present here.
Okay.
Okay, then you can see these nodes are actually going to the negative terminal of a comparator.
Yes.
Okay,
Yes.
and the working of this comparator is in this way, that let's say there are two terminals and I have connected two voltages Vx and Vy. Vx is connected to the positive terminal, Vy is connected to the negative terminal. Okay, so the output
Yeah,
of the
okay.
comparator will be 1 only when Vx is greater than Vy.
Okay.
Correct? So
Okay.
this logic we are going to use in our flash ADC. Okay, so now I have connected my Vy, or the the inverting terminal, to the reference voltages that has been generated.
Okay, sir.
Okay, so let me pick any one, let's say D1. Okay, so the negative terminal is connected to 2 volts,
Yes, sir.
right? And the positive terminal is actually connected to incoming signal, right?
Yes, sir.
So when will this output be 1?
Vx greater than Vy?
Correct. Vx greater than Vy or Vin greater than Vn ref.
Then,
Correct. So that's what I am observing, that which comparators are giving me 1. It means in which of the cases is my V input greater than the V reference. Okay. So what we observe that V
Okay.
input is given as 10.13 to us. Okay. And here I have listed my reference voltages.
Okay, sir.
Okay. So 10.13 is going to lie between 10 volt and 8 volt.
Okay.
Right. So it is going to
Okay,
lie.
sir.
Yeah, it is going to lie somewhere here. So it means the D5 bit. Oh, sorry, wait. It will lie somewhere between here, 12 and 10 volt. Right. It is 10.13.
Okay.
Greater than 10, less than 12. So
Less than 10.
yeah, so it means D6 will be 0 because 12 volt reference is greater than V in. Okay. But D5 will be 1 because only in this case the V in starts to become greater than the reference voltage.
Yes.
Correct. So after D5 is 1, you can easily state that because looking at this trend, the Vref per node decreases.
Yes.
So if V in is greater than 10, it means V in is going to be greater than any of these.
Yes, sir.
Correct. So all these bits will also be high.
Hi. Okay.
Correct. After finding out these bits, what we are going to do is we are going to pass it through a 3-bit priority encoder. Okay. And the property of a priority encoder is, so whatever highest bit is set, okay, so that bit gets encoded into binary.
Okay.
Okay. So in our case, D5 was set. Right. So the output is going to be 5.
5.
And 5 in binary is 101.
Yes.
Okay.
Thank you, sir.
Yeah, sure. Okay. Then there was another question. Okay, so then there is a question that, okay, in 2 complements, how the negative number can be represented using 2's complement. Yeah, so let us say you have a number, okay, we covered it in, let's say you have a number, let's say -5, okay. So the first thing that you do is you find the binary equivalent of this number. Okay, find the binary equivalent of 5. Okay, then you take the 1's complement. Okay, because to arrive at 2's complement, we basically take the 1's complement, then we add +1. Okay, that will give us the 2's complement, right? And that is basically your negative number. Okay, so there are different forms of representing a negative number. So one of the form is okay, but I don't know whether this is an assignment question or not. So okay, I'll tell you a generic statement. So what you can do is, so there are different forms of representing this binary numbers. So one of the form is like you can use a, okay, but I am not sure so whether to be discussed or not, because what we are supposed to discuss is whatever is covered in the session. But yeah, otherwise you can put this in the forum if that's fine. But yeah, so if let's say you are given a number, let's say x, okay, and you have to represent it in 2's complement representation. So the first thing that you should do is you take the yeah, okay, you are referring to the sign bit, then yeah, you can take the sign bit. Let's say you have put 0 there, then you take the 1's complement for the complete set. Okay, and then you add +1 to it. Okay, if there is an overflow, okay, then you need to deal it with by complementing it again, else whatever is the value that you should arrive at. Does that answer your question? Because I can't take specific examples. Okay. Is there any other question that needs to be addressed? Okay, so I'll be here around, so let me know if anyone has any doubt in any question. Yeah, if anyone has any doubt, then they can let me know, else we can close today's session.